All right, everybody, this lesson is transformations of exponential and logarithmic functions. Go through full details here for transformations. Really, transformations are the same regardless of what shape you're starting with. But I'll go over it in case you need to review it. So this is the handout that you'll see from the Jensen site. I'm going to get rid of some of the parts of this. There we go. Get rid of that thing that went away. So first of all, I want to just sort of point out we're talking about fundamental shapes that you're kind of starting with. And he has these listed, but really these are just exponential functions with a transformation applied to them. And so just to back up for a second here, of course, regular transformations you've seen before are your A, your K, your B, and your C. Sometimes people use P and Q, whatever you've seen. That doesn't matter. The location of the numbers that those variables would take on what's important, of course, right? So I'm just going to make a note here. These are not really fundamental shapes. They are really just A equals -1 transformations. Which means that we can get rid of the -1 versions, so the 3 and the 4. So this isn't really a fundamental shape. This is just this one here, flipped upside down. We'll talk about the transformation types in a second. And the other one, 4, that's not really a fundamental shape either. That's just this one flipped upside down. All right. So I suppose I could have color coded that better, where I could say or purple or something like that. All right. So that's just that one flipped. All right. So modified handout that I'm posting. I left room here for describing all of this stuff. So you got your A, B, C, and your function, Y value, you're graphing or thinking about, is kind of your, think of like Y equals X, and then think about F at X being changed, so it can be multiplied by a number in front. It could have a number way outside added to it. Essentially, you're just adding to the Y value, or you can operate on the X, but forward the function happens. And that's with the K and the D are there, right? So let's put that up slightly here. Sometimes people use square brackets to distinguish, but obviously the bracket goes with that one, and then the bracket around the X, the -D, there. So let's go through each of the transformations just as a review. So this one here, going here. So this one here, give yourself some room. That is your vertical stretch or compression. And we'll use short forms for this. But anyways, the stretch is if you have an A value greater than 1, essentially, or A between 0 and 1. Indentation between 0 and 1. That's just the positive versions of things. If you had negative versions of this stuff, then it would be a flip, a vertical flip. So it's a vertical flip. If A is negative, i.e. the equivalent here would be, in other words, you have A being less than -1, or A between 0 and -1, keeping the number line logic in mind here, right? Picture a number line, and if you had 0 and you had -1, A is between the two, right? So it's there. Okay, so I always try to keep my inequality statements the same order direction as the logical number line. Let's go to the next easiest one over here. Right, the C value there is going to be your vertical shift. And if you had C greater than 0, it's up, and if C is less than 0, it's down. Kind of the easiest one of them all. And keeping going here, I can mention that I kind of like to just think of this in a simpler way, where I coined the phrase in the past with grade 11 classes, if you had me, brackets backwards. I'll try to give a little bit of an explanation as to why things are backwards as part of this. I'll just show how it all works. So the logic of this is that you're operating on x before the function happens. So we need to think of what x, the new value of x needs to be, so the function's operating on the same value it would have been operating on. Okay, so think of the new value of x. The value of x needs to be so the new value x we need to have for the function Cn for short there, to have the value it would originally have. So the value it originally had. Okay, so if you're thinking about that, from in there, we have our k value. Our k value is our horizontal structure function. Forms there for that. And so you have for the compression, kind of backwards logic, right? You have like a greater than 1, or greater than the less than, sorry, the negative 1 for the horizontal flip version, but I'll write that in a second. Actually, I'll write that right now. So, or a less than negative 1, horizontal flip. Just as an example of that, so what I mean by this value would have been thing. If you had a function operating on 3x, well, think about the fact that x itself would have to be x over 3 in order for, right, this would need to be x over 3 so that you have the function operating on it, but originally would have, whatever x was, right? So that's kind of why it has the opposite of what you expect. You put in a 3 expecting, oh, it's going to get 3 times as wide, but that's not what happens. It gets 2 times as narrow, or divided by 3 essentially. All right. Hopefully that kind of demystifies the weirdness of that one. On the other end of things here, you have to be less than 1 or 0, kind of like in the vertical stuff, but it's just opposite, okay, for stretches instead of compressions. And then of course, for you have your -1, between -1 and 0, right? For the horizontal flip versions of things, those stretches. So we've got our k value all mapped out, and then of course, similarly in the middle here, the negative d, I'm going to put it in quotes. So the negative d is your horizontal shift. And so, numbers wise, I'm going to show, and we'll talk about how it makes sense. Okay, so this is how most people would logically think of this, an easy way, where you just look at that and say, oh, it's going backwards. And so this is actually to the right. So like BB for short, brackets backwards, you're going to say, hey, this thing is to the right, shifted to the right. The other version, x plus 3, and say, oh, well, that, I think it'd be to the right, but of course, brackets backwards, and so it's to the left. So, yeah, logic to do with that is, of course, like I said before, x for this case here, x would have to be 3 more for the original to be what it, for this function to be operating when it would have been what it would have been originally, right? So leave it like that, and then you can see that if you had f of x minus 3, the actual numbers you can see, and if you say, okay, this is equivalent to our form f of x minus d, then you can see here that negative d would have to equal negative 3. So in other words, d would equal positive 3, and that's what textbooks think that makes sense. In order to write it mathematically, it does make sense, but our brains just don't quite work that way as humans. But then the textbook would say, oh, see, d is positive 3, therefore it's to the right. But that's just an equation that doesn't really sit well with a curious mind. You want to kind of know why, rather than just because the formula has that value. So I hope that helps you. Oops, that's not what I wanted to do. Hope that helps you feel good about why it's really true. Just wanted to prove this stuff. I don't know, I guess it's fine. There's your K and your K and your D and your all the things to see up there. All right. So here we go. When you're actually doing transformations, I'm going to show this in a little more detail than the original file Jackson had. But I'm going to show, I like the way you show the equation in the top row, so I'm still going to do that for sure. But I'm just going to show the steps along the way, and also require on assessments that you show at least some of those steps along the way. Show the original, show it stretched, and then show it, shifted. I usually use shifts together. So that's what I'll show. Makes it less cluttered of a graph, right? So all you have to do is just pick numbers, of course, file in some numbers for this. So let's just pick -1, 0, 1, and we're going to point out, as he did, as Jensen did on the site, the horizontal asymptote. If there is one, and we should point out where it is and maybe where it ends up. If it moves. And so when you just plug in values to this, show, of course, you're plugging in a -1, right? So it's I'm just graphing. Notice here, I'm just graphing 3 to the x for now, right? So this is just your original, right? 3 to the x. So 3 to the power of -1. It's pretty easy, but I'll just show here. On, I have to use the mouse to do that. There we go. Now I can use this one. So we have 3, and it's used to the power. I'll just be careful here. -1 brackets to make sure I'm doing the right stuff, and it is 0.333. All right, so easy enough. 0.333. So let's just do 0.33 there, and then 3 to the power 0. Of course, it'll just be 1, and 3 to the power 1 will just be 3. And you're probably familiar if you typed in 3 to the power -10, you get 0, 0, 0, 0, you get closer and closer to 0. So you have a horizontal asymptote. This isn't the lesson on exponential functions, it's just transformations of functions. So if you need help with exponential functions yourselves, go back to that lesson, of course. So for the transformations aspect of things here, we're going to go through this. We're going to say, okay, well, if we have this transformation we're trying to do, then really we are looking at something like 2 of fx, right? And so we are going to be multiplying. This is, by the way, of course, the y value. And so essentially we are multiplying the y values by 2 because the function f of x is the y value, right? So when we graph this out, we're going to have a 2y there, 2y, original axis. So original axis, horizontal axis, good information. And we're just multiplying all the y values by 2, so easy enough. Y values multiplied by 2. Show that nice and clear what we're doing. And 0.66 and 0, 2. 0 times 2 would also be 0. So the horizontal aspect stays the same when you have a vertical stretch. That 2 2 is doing, of course, this rate value, right? And then moving on to the next one, you can see we're doing the horizontal shift stuff, right? So we're looking at, I guess I'll put the original part there, the original shift we did first as well, the transformation we did first, but it's x plus 4, right? And so you should be saying, okay, I know that's to the left. And so because that's to the left, all we're doing is actually shifting the x values to the left. Right? It's the easiest way to kind of think about it. And of course, we have our transform function that is stretched vertically by factor 2 that we're operating on, so it's still a 2 log. So these apply, right? 0.66, 0, 2, and 0. I shouldn't maybe have said the horizontal asymptote yet, but we're just shifting this thing left or right. Of course, the horizontal asymptote is not going to change, right? We're just moving the layered function to the left. And I immediately pause the calculation work and show the graphs as we go along too. So at -1, we have our 0.33. Hard to fine tune there, but we've got our 0, 1, catch up on the graphing here, 1, 3. And so we have numbers like that. Like I said, if you graphed a number like -7 or 10 or whatever, like I said, it would be very, very small, right? 0.0 something. So you have to try and graph this thing. It's a little tricky on the smart board here, but there you go. There's your original function. So that is your f of x is equal to 3 to the power of x. Right, so that's the original function. We are graphing. It goes both ways, and it's pretty obvious to have an asymptote there. Also, of course, if I have one, I'll use that one. I guess I don't have it ready to go, but we've got a horizontal asymptote at 0. Pretty good. You can list that as your horizontal asymptote at y equals 0. A lot of people say like y does not equal 0. Well, you label it as horizontal asymptote, that's totally fine. So that's the original, and then we're going to be graphing a new one where we're going to be vertically stretching that thing, right? And so vertical stretch, you can just look at the graph, it's pretty easy. It's going to be double that height and double that height. But of course, that goes along with my numbers of, you know, the one. So double stuff to check work here. Doubling, of course, the 3 will be 6. Sorry about that. And 0, of course, double 0 is still 0. So if you think about the double of the 0.66, or the 0.33 became 0.66, sorry, and the decimal 0 became a slightly bigger decimal 0, but yeah, so when we graph this stretched one, red one's just slightest bit over top of this one, then the difference gets a little bigger as you go, of course, because the multiplication factor. So that one, f of x equals 2 3 power of x. Now the numbers are fixed. So it's proper. So it's a good idea to actually do table and graph simultaneously to catch errors. So I've modeled that nicely for you. Probably not. All right. So to the left now, right? So to the left here, let's take our x values and we are shifting those to the left. We're taking away 4, right? So take away 4 from the -1 and -5, and then -4 from that, and -3 from down from the 1. Okay, so I'll do this one in 3. So -5. Actually, I'm going to keep going with the table here, and I'm going to show both shifts together. It's going to be pretty easy to show -4 here. So I'll just show the arrows for now. -4, 1, 2, 3, 4 steps, and 1, 2, 3, 4 steps. 1, 2, 3, 4 steps. Right. So we've got those shifts taken care of. It's not too hard to do the other shift while we're at it as well. So we have a -5, right? So the y is going to get dropped down by 5. So we're looking at what we had there, the 2y, and it was dropped by 5, reduced by 5. And of course, we had that x -4 status, or the result that we were at. So I can fill those in. We've got our -5, -4, -3, our horizontal asymptotic information. Don't throw in a 0 there because you have to be careful, things are change here. So we're dropping it down, right? So we're reducing everything by 5. So if you needed to do it, you could do the 0.66. I probably would, to be honest. The 0.66, just to be safe, right? Take away the 5, giving us the 4.33 or whatever rounding to, right? So 4.33 would be the closer one if I had kept 0.666 is the one. Anyways, so let's get that in there. So -4.33. So I'm going to stick with that. My graph's going to be black, so it'll all match. -4.33, and then dropping the 0. Darn it. Good thing I could do these. 2 and 6. Didn't notice that I'd written that wrong, but of course it's the new y values there, right? Changing the x's and then grab the wrong y values. All right, try. But the 2 dropping by 5 brings us to -3 and 1. -3, 1, that's the 6 dropped by 5, and then the 0 dropped by 5 brings the horizontal asymptote all the way down to -5, and so we're going to drop by 5. So 1, 2, 3, 4, 5, all the way down to there. 1, 2, 3, 4, 5, down there, and from this arrow, 1, 2, 3, 4, 5, all the way down to, so the top of that one, 1, 2, 3, 4, 5. Yeah, I think I got that right. Just double checking. And of course, our passing is going to all the way down as well. 5 steps. So I'm just going to that one. Hit 1, 2, 3, 4, 5. So you can see that this point that was sort of 0.66 above is still 0.66 above. The one that I was double checking to make sure it was good. I like to put the dots where I'm going to be drawing at the end of these arrows. Do a little dry run with the asymptotes there. I'll show it with the mouse, I guess. I'm going to sort of run my pen, hover it over the surface a couple times and draw that, and then go for it, draw it real. Right, so there's my asymptote. It'll let me write instead of grabbing the arrow here. There's my asymptote going through there, through there, through there, and up. So that is the total result. Here we got our f of x equals the 2 and the 3 to the power of x plus 4, which is sort of inside the bracket. Brackets aren't necessary because it's up in the exponent. So 1. Okay, so that's how I like to see it, where you've got the original and then the new shape from the stretches or compressions. I would do both stretches and compressions, so only one in this case, only the vertical, but do both of those as new shapes. So you'd have original and then stretch vertically and then stretch or compress horizontally. So 3 parts, and then you can just do your shifts all in one step like I did there. It makes a nice result. So I'm just going to make that thicker so it stands out as the result, of course. Something like that. Okay. So if you look at the Jensen version of things, that's this red one, where it's been changed, the shape's been changed, and it's been shifted. All right, so next one, I'll try and make less mistakes here, but no promises. So starting with that same starting graph, of course, it's still a 3 to the power of x function, and we're going to be graphing the negative 3 to the power of x first, so you can tell that we are multiplying the y value by a negative. So minus, and we have our original up here, the x, so we got 1, 0, 1, and the horizontal aspect information. It's not going to change by just multiplying verticals by a number, because 0 times that can still be 0. Should be good. And so these are just going to get multiplied by a negative here, right? So it's negative 0.33 and the negative 1. Right. So that is shown by having, which I used before. It really matters, but I used red first before. So maybe multiplying the y's by negative 1. Right. Yeah, so I guess I should put my original on here. So we got our 0.33, got our 1, our 3, we got our asymptote. I'll draw it in a second. There is our f of x function itself, where it's just 3 to the power of x. Asymptote shown there somewhere. It's enough. So there you go. And then we can graph the new one, which is going to be at negative 1. We're going to get negative 1.3. And that 0 we get negative 1. And at 1 we're going to get negative 3. So you can see this is the upside down. Negative 0.00, sorry, 0.0001 or whatever, become negative 0.00. Underneath the asymptote this time, skimming along and doing its thing here. I didn't go quite as far up, so I don't on the screen, but there it is. So that is, of course, your g of x function. They have labeled it as g of x equal to the negative 3 to the power of x. Right, so next step here, we have our horizontal information, and that's going to be actually the horizontal stretch. Right, brackets backwards, half should be compressing things, but it's stretching it. That's just what it is. How it works. So we are going to be taking our x values. I'll show it like this. We're going to be actually multiplying by 2. The opposite of dividing by 2, the opposite of that. So we're multiplying by 2. Carefully get these right this time. Hopefully multiplying by 2. That, multiplying by 2, and the horizontal asymptote information will pull that as we go. Right? So just horizontally changing things. That's not going to change the asymptote. And our y values are all the same. So I'm graphing right now, plotting and then graphing a regular x, but it's multiplied by 2, right? So it's 2x. And then our minus y's are just tagging along for the ride. 3 to the negative of it, and so on, just like before. All right. So asymptote stayed still. It's still at the value of 0, y value of 0. Yeah. We got to put x equals 0 there before, but it did it right. All right. Like that. Done. Let's graph that one as well then. So let's graph the green one here where we're at negative 2 and negative 0.33.
I heard you your photograph.
Oh, thanks. Negative 2 and so you can see that it's like that's height that's stretched over, so it's going to be wider. The 0, negative 1 didn't switch at all because stretching is 0 times anything is still 0. And then instead of being over 1, it actually is over 2. 3. So we've got a graph here. It's essentially this almost looks the same along the way here. It's going to go through there, and then it's going to go this one, and then it's going to go more gradually, like that. So that's your g of x equals your -3 to the x, the 1/2 of the x. Horizontally stretched by a factor of 2. And then finally, the easy one at the end here, where we're just adding 4 to the y's, right? So adding 4 to the y's is vertical shift up 4, nothing there, and so it's going to have the negative y value add plus 4, and we have our regular specs we had already. Well, yeah, just doing a video from our class. So, okay. All right, so hide away before people still find me. All right, so we are adding 4 to things. I'll skip the calculation there. You can add 4 to a number. You get 3.66, and add 4 to that. You get 3, add 4 to that, 1, add 4 to that, 4. So of course, all knots would have shifted 4 steps. I'll show that first. Up here, horizontal asymptote up there, and we're going to shift everything up. So we're going to shift our new station at 2, or just under the asymptote up there, and we're going to shift this one up 4 steps, right? So that was 1, 2, 3, 4, and then 1, 2, 3, 4 up to there. And this went up 4, 1, 2, 4. I wasn't looking at the table for the numbers as much as just shifting up 4, but you can confirm, of course, I shifted up 4 to item 1. There it is, item 1, of course, right? So it all makes sense. And then you can draw. So we're just skimming the horizontal asymptote, going through our spots like that. So there's our function overall. We've got our -3, 1/2 of x, and then the whole thing outside of all that stuff adds vertical shift to 4. That gets emphasized being our result. Let's just go to that level there. It's enough. All right. So that is the blue one here on the solution that was originally posted there on the Jensen site. And last but not least, we have 2 more to do here. The log function. So for the log function, just get my calculator going here. We could, of course, just plug in numbers, but we have to be mindful of what we're allowed or what we can put into it. The calculator will remind you though, like if you try to do log of say like -2, I'm going to have to divide by log 3 because we're talking about log base 3. But it wouldn't have been able to do it either way. It's going to give me a non-real answer. It's going to say, you know, that doesn't work. You can't put that number in, right? You can't put a negative in. It brings the cursor near the problem. It should have really had it right there. But if I got rid of that, it would be like, no, log 2 basically is fine, but log -2, no thanks, right? Log of 0, same thing. Can't do that, right? There's not, we can't have, yeah, an exponent that'll give 0 as a result. So 3 to the power of something gives you 0. Well, it would have to be like -infinity, I guess, but that's not what we're talking about. We're not talking about numbers in the real number set at that point. Infinity is more of a concept, really, right? So we could do a table of values, but we just have to be careful what we put in. So we could put like, I don't know, log, we could put in a, what do I want to put in the end? Show you, I'll do that. I'm going to put in a 1. Okay, so if I put in log of 1 base 3 divided by log of 3, then it's going to spit out an answer of what? Well, that's going to mean what number, so that you get 3 to the power of the number we're looking for, it gives you a 1. Well, that has to be 0, right? So boom, there it is. So we could make table values. I'm going to draw on our knowledge that we're talking about the inverse, right? To absolute inverse of this is the log function. Right? Is this thing. So, I guess the arrow right there, there's the actual inverse I'm talking about, right? And so I can just go ahead and put the point, the reverse version of this, 0.33, and then so I'm going to put this 0.33 all in. 0.33, 1, 3, 0. Corresponding x value, minus 0, 1. That's going to be, in this case, instead of horizontal asymptote, of course, we're switching x and y, so that becomes a vertical asymptote. Right? I did skip over one thing at the bottom of the page that I want to go back and show as well, just like with the exponential one. Jensen included this as like other key shapes, the 3 and 4 here, but that's really just when you have a k value of less than 0 and negative k value. Right? So those aren't really new shapes, those are just k less than 0 transformations. I'm supposed to say just, as I said it. Anyway, so the 3 and the 4 are not fundamental shapes. They are just mirror images of 1 and 2 vertically, right? So you can see that 1 would mirror image to 3, and then 2 would mirror image to 4. But that's just like a horizontal transformation. K is negative. So we think of those as shapes to remember starting fundamental shapes. It's silly to do that. Really, 1 here, the red one, and 2, the green one. Those are your fundamental shapes to start with. Just like when you first did transformations in grade 10 quadratics, you had your regular quadratic shape. Didn't bother memorizing the upside down version because that's just one of your transformations. All right, so here we go. We are going to transform the -4 first. So we know that's going to be a vertical stretch and flip. Vertical stretch and flip. So we know what to expect, which is nice. We're just going to be graphing and doing that one first. So let's do that. Let's do the x and 4y. So obviously we are just multiplying the y values by 4 or negative. Right? Very nice about it. So we are going to have the x values not changed. This log function. Stick to the other side. I'll come back to that. Think about it a little bit. So we're going to have times -4. So it's going to be +4. Half the +4 obviously it means +4, but and then we have 0 times 4. We have the 1 times the -4. And there we go. Right? So our vertical asymptote of x is equal to 0. So yeah, I think I like how that vertical asymptote x value is 0. Paper copy, I looked at it written the other way. This is better. All right, so let's graph some stuff and graph the original transformation. Original. Need to go over to x 0.33 down. Go and up. 0. We need to go 3 and up 1. Right? And if we did look at very small numbers, 0, 0, 0, 0, or whatever, it would skim just on the side. There's a blaster that as well in a second. It's like the wrong way there, but it's hard to skim that line past the 0.33. But I'll try. So that's just your f of x, and that's your log base of x. Right? Then what's next here? We're doing the vertical stretch step and flip. So the 0.33 was down 1, instead of 0.33 up 4. 1, I need to be at 0 still, because multiply by 0, or multiply 0 by any number stays at 0. And 3 are going to be down 4. It's a similar shape, but stretched, taller up and down vertically. We have our function. So that is the f of x, and we're talking about negative log negative 4 log base 3 of x. And then last transformation for this one is, or last one is, yes, so we went back, but we just need to go up 2, right? So we just need to go up 2. So for that one, let's go up 2, vertical shift. And so our x information, 0.33, and so on. So 1, 3, 0, because we're not moving sideways at all, right? So it's not going to change. So our vertical aspect is not going to move. And we are going to go up 2 from all this stuff. So the 4 is going to get 2 added to it. 6, 0 is going to get 2 added to it. The -4 is going to get 2 added to it. Those should be my numbers. And obviously we're looking at our x value still, because we're not doing anything to x here at all. That's fine. And then we have our -4, 5, but then we're adding 2. So we just get our table of values, and the graph makes sense as well, where we're just adding 2 to everything, right? So I just have to add 2 to everything and make it happen. So here we go. 2 to that. I'm supposed to be at my new one. Right? That's a common mistake that students make sometimes too. So that's a possible thing to watch for. Go for your new shape. Up, 2 everywhere. And again, put my dot, trace, run my pen along that a couple times, and then be like, okay, so I'm ready to go. And like it. See through the projector screen here. There we go. So that is f of x equals -4 log base 3 of x, and then it was plus. Right? Right? So make all that bold so you can tell which one's the final one. I like it. And last one here. Last one. All right. So starting with that function there, we are going to do the negative x. This is first, so we know that's a horizontal flip. Technically, horizontal stretch compression, but there aren't any stretch compression flipping it, right? So it's going to be negative x, negative 0.33, negative 3, and negative 0, I suppose, for the vertical, so it wouldn't have changed at all. Wonder I did it backwards, I guess, the last 2, 0, and so on. I did originally, that's why I did it. I guess, anyways, all good. Happened. Yeah, so this is our y values, and so we have our -1, 0, 1 vertical asymptote information. So graph the original. Original is referred to it here, over 0.33, and we're down 1. Over 1, 0. Over 3, up 1. And every vertical asymptote, always asymptotes, actually still. But that, they only wait 1. All right. So we've got original draw here, something like that. X is our log base 3 of x. And when we do our negative x, first transformation, we go negative. And down 1, so negative 0.33. So you can see we're just a mirror image on the other side. So it becomes easy to sort of think of that as that, or you could look at the table and say, oh, negative 1 up 0, negative 3 up 1. 3 up 1 is just your imaged along, and your imaged 3 up 1. So because I'm looking at that mirror image, I notice my first little incorrect spot for my duck. Skimming along the other side of it, coming up and going through and out. Right, so that's my f of x log base 3 of negative x. Then we have to next transformation here of the, think about this, right? Backwards, so it's a horizontal shift, but it's the left to, right? So that means we're going to be doing our negative x is going to have 2 taken away from it. Shift to the left, the y value stays tagging along the right, original values. So the -1, 0, 1, and our vertical asymptotic information, which is going to change this time, right? So moving that thing to the left here. So let's do that. Oh, I'm thinking about it here. Back. Go. Left 2 steps. Boom, boom. That's where my new vertical asymptote is going to be. And let's do it. So we're going to have 2 taken away from all this stuff. So it's going to be a negative 2.33. And the negative 3, and the negative 5, and of course, 0 gets negative 2. Shifted it over. And so that's our x equals negative 2. Of course, vertical asymptote. So that stuff can be done easily enough. And then we have a vertical shift, right? Up, down, 4. And so let's do that at the same time. So we're going to take this step, we're going to subtract 4 from it. So subtracting 4 becomes -5, -4, -3, and we have our vertical asymptote information not changing from that negative 2 that it had become. All the other x values are just tagging along, changing vertically. So let's show both of those and we'll be done. So we just have to move left 2 and down 4. So from my red one here, left 2, down 4. Left 2, down 4. From here, left 2. And then left 2, so just to the left of the asymptote, to just to the left. Down 4. Here's where my numbers are when I draw it. And so the this one, I guess I could have done is go, and I'm ready to go here. Something like that. Put it down a little better, I suppose. By the end, be able not going back down. But doing this long enough. So yeah, there's our. This is the bottom here. So these are actually g of x, right? So g of x. We've got our where we have log. Log x plus 2 minus 4. So I'll just change these things. Oops. Negative is inside. Log base 3 of negative of x plus 2. All good. And that's pretty much it for this lesson. Any questions? Come see me, of course. Thanks for watching.